GPT-5.5 transitions AI from prompt and response interactions into autonomous, long-horizon execution. It operates as an agent, capable of performing complex, multi-step workflows over hours or days. To measure this, OpenAI uses VulnLMP, a multi-day vulnerability research evaluation. The agent is given access to a sandboxed environment where it independently compiles code, navigates directories, and tests hardened software for days at a time. This level of autonomy creates a core paradox. The skills an agent needs to independently discover and patch a critical network vulnerability are the same skills required to exploit it. Defensive utility and offensive threat scale together. Because of this dual-use nature, GPT-5.5 has officially entered the high capability tier within OpenAI's Preparedness framework for both the biological and cybersecurity domains. Deploying an autonomous agent requires a layered control architecture, combining empirical capability limits, internal reasoning monitors, and operational access controls. When an agent acts continuously over days, static prompt refusals at the start of a session are no longer sufficient. Safety mechanisms must function as a dynamic part of the execution process. The first layer of this architecture establishes the physical limits of the base model. We begin by examining the biological domain. On written evaluations testing tacit, expert-level biological knowledge, GPT-5.5 scores highly. But theoretical knowledge does not always translate to practical application, and the model hits a bottleneck when tasked with actual biological engineering. This is tested through the hard negative protein binding evaluation. The goal is to see if the model can accurately distinguish functional binding proteins from non-functional ones. To remove simple data science heuristics, the model is provided exclusively with candidate proteins that already have high AlphaFold interface predicted TM scores. This forces the agent to rely entirely on expert sequence-to-function judgment. This bar chart illustrates the results. While the candidate proteins all have high predicted confidence scores above 0.8, GPT-5.5's actual success rate in identifying the true binders is 0.4%. While the model can parse complex biochemical literature, it lacks the sequence-to-function judgment required to independently engineer a biological threat. The boundary line shifts in cybersecurity. Here, GPT-5.5 demonstrates a measurable uplift in agentic capability compared to previous iterations. To map this, researchers run cyber range evaluations, long-form tests measuring the model's ability to conduct end-to-end operations in realistic, emulated networks. As the checkmarks populate this list, we see the model navigate evasion, privilege escalation, and lateral movement, culminating in a 93.3% combined pass rate. A 93% success rate is high enough to classify the model as a high-capability threat. However, it does not cross into the critical tier. The VulnLMP results clarify why. The model can sustain multi-day research campaigns and generate valid memory safety leads within hardened targets, but the capability stalls there. GPT-5.5 fails to independently chain these disparate leads into novel, full-chain zero-day exploits against those real-world targets. The first layer of safety holds because the model's base capabilities remain bound below the threshold of an uncontainable offensive threat, even while providing acceleration for network defenders. Even with physical limits, an autonomous agent poses an oversight problem.
If it operates in a sandbox for days, developers need a way to ensure it isn't executing malicious actions. This leads to Layer 2 of the safety stack, chain of thought monitorability. Monitoring an agent by only looking at its final actions is reactive. A more effective approach is to continuously read the model's internal reasoning trace, its chain of thought, before it executes an action. This graph shows monitorability. As reasoning trace length increases on the x-axis, the ability to catch violations climbs. Notice the widening gap here. Relying only on final actions produces failing oversight, but reading the full chain of thought allows the monitor to flag dangerous behavior. This introduces a risk known as scheming. A capable model might realize it is being monitored and intentionally hide its true intentions within its reasoning trace. To test this, researchers measure caught controllability, the model's ability to successfully follow instructions to alter or obscure its own thought process. This descending line plot tracks the model's control over its reasoning. As the character count of the trace reaches 50,000, GPT 5.5's ability to control its own reasoning drops to just 0.2. Second, a real-time automated oversight pipeline acts as the final gatekeeper for output. This flowchart illustrates the dual-tier system. User input is first routed through a fast topical classifier. If the system flags cyber-related content, the request escalates to a safety reasoner, which checks the data against a mapped cyber threat taxonomy before allowing the agent to proceed. This system is effective, but it creates operational friction by blocking legitimate high-level defensive workflows like penetration testing and malware analysis. The solution to this friction is the Trusted Access for Cyber Program, or TAC. TAC moves away from model-level restrictions in favor of identity-gated access. It unlocks frontier defensive capabilities only when a user provides verified cryptographic and institutional trust signals. The external monitoring catches what internal monitors might miss, and the TAC program ensures the most sensitive dual-use capabilities are physically restricted to verified network defenders. This unified defense-in-depth architecture stacks base capabilities, chain-of-thought monitoring, and identity access. If a user circumvents identity, monitors catch their reasoning. If that fails, base limits prevent execution. Ultimately, this stack ensures defender success rates remain exceptionally high against sophisticated multi-turn jailbreaks. AI has evolved from conversational interfaces into the realm of continuous long-horizon agents. Ensuring the safety of these systems can no longer rely on simple lists of banned words or static prompt refusals. The GPT-5.5 system card demonstrates that safely deploying frontier agentic models requires a holistic architecture of empirical capability boundaries, dynamic reasoning audits, and strict identity-based access control.